Hello friends. So today we are going to discuss few questions from the year 2003. So there are a total of 3 questions from the year 2003. So in the first one, it is given that for a positively charged particle moving in xy plane, initially along x-axis, there is a sudden change in path due to presence of electric and or magnetic field beyond point P. The curved path shown in xy plane is found to be non-circular. Which of the following combinations is possible? So in this question, we are given this figure, and from this point P, this traces a curved path. Okay, initially it is in a straight line, and here it is important to consider that this curved path is non-circular. And second thing, that it is moving in xy plane. So if it is only moving in xy plane, then there won't be any net force along the, you can say, z direction, that is k unit vector. And secondly, because it is moving in non-circular path, and or we can say talk its reverse, that if a body is moving in a circular path, then only magnetic field acts perpendicular to the velocity. So it is a non-circular, so it means both electric and magnetic field are acting on this particle. So we start from there only. So we can say the particle motion is constrained particle motion constraint, and it is given the particle moves only in xy plane. Particle moves only in xy plane. So based on this, we can say there cannot be no net force in z direction. Or which basically means k unit vector. And second thing, we can also draw an important conclusion that any, you can say, magnetic field component along x-axis does not have effect, because the particle motion is because of the cross product of velocity and magnetic field, that will result in 0. So we can say any magnetic field component along x-axis, which basically means I unit vector, does not affect the particle's motion. The particle's motion, because it is given that the initial velocity vector is along I. We can say since velocity is along I vector, and our v cross b would be 0, 0 for if it is having a x component along y-axis. So this is the first part, and second part we draw on the base of the circular path or non-circular path. So in the second case we are given non-circular path. So non-circular path. So let us discuss first our circular path. That will make non-circular path absolutely clear. So you can say a circular path occurs when only a magnetic field acts perpendicular to the velocity. And in the question it is given that the path is non-circular therefore both electric and magnetic fields are present. Or we can also say that the magnetic field is not purely perpendicular to velocity, or magnetic field is not purely perpendicular to velocity. And for the force analysis we are going to use the Lorentz equation. So that is pretty standard equation. So you can say for force analysis F is equal to Q E plus V cross B. And like I said, for the circular path the magnetic field, only magnetic field should be existing. So based on this we can clearly understand that the electric field cannot be equal to 0. So option A and option C cannot be the correct one. So you can say that we have our option A. It is given that the electric field is 0 and magnetic field is our Bi plus Ck. And if we find out the magnetic force, which is our Fp, we are going to get Q I unit vector cross product Bi plus Ck, and this gives us minus Q VCJ. So it means force is along, purely along y direction, that is minus J. Fp is along minus J, or we can say y direction. So it means there will be a circular motion in xy plane. Circular motion in xy plane. So it will be having a circular path. So this basically means it is going to have a circular path, and in the question it is mentioned that it has to be a non-circular. So option A is incorrect, and let us come to the next option, that option number B. It says that our electric field is equal to AI and our magnetic field is our CK plus AI. So once again we find out our here I forgot to mention that the electric force is equal to 0 because the electric field is 0, so electric force is equal to 0. So electric force will be equal to QAI and our magnetic force will be equal to Q, we have our VI cross product CK and AI, and this gives us that magnetic force will be equal to minus QVCJ unit vector. So therefore net force will be equal to our QAI minus QVCJ, and in this particular equation there is no K unit vector, so therefore motion is in xy plane. XY plane, and obviously electric field is present, so electric field plus magnetic field both are present, so it will be having a circular non-circular path. So we can say path is non-circular. Now we come to the option C. Once again here electric field is 0. We are given that our electric field is 0 and B is equal to CJ plus BK, and electric field is 0, so we can say the force due to electric field will be equal to 0 and force due to magnetic field will be our Q. We have here VI cross CJ plus BK, and this gives us QVCK unit vector minus QVBJ. It means in this question the electric field is also 0 and the force also consists of a K vector, K unit vector rather. So we can say that force has K unit vector component. Therefore particle will leave xy plane. Particle will leave xy plane. So this cannot be correct one, and now we come to the final part, that's a D option. Option D, we are given that electric field is in I direction and our magnetic field is CK plus BJ, Once again, we can write that our force due to electric field will be equal to QAI, and force due to the magnetic field will be equal to QVI cross CK plus BJ, and the force of the magnetic field will be equal to minus QVCJ plus QVBK. So no doubt, in this case both electric field and magnetic field are present, but there is a component of magnetic field which force component which is in K direction. So we can say force FP has K component, K unit vector component. Therefore, it will leave XY plane. So this option is also incorrect. So D option is also incorrect. Only option correct is option number B. So option B is correct. Come to the next question. It was also asked in the year 2003, and it says that a current carrying loop is placed inside a uniform magnetic field in 4 different orientations. Arrange them in the decreasing order of potential energy. And so there are 4 orientations, and the area of the loop or cross-sectional area of the loop is arranged in the different way. Like in first case, the magnetic field is toward the right, cross-sectional area unit, its vector rather, is along to the left. The second, there is 90-degree angle between the two. In the third, there is certain angle which is less than 90 degree, and in the fourth, the angle between the two is greater than 90 degree but less than 180 degree. So it is based directly on the formula, and we know the potential energy of a current loop inside a magnetic field is represented by a magnetic moment and its magnetic field. So potential energy of a current loop in a magnetic field, that is given by the equation U is equal to minus m dot B, or which is basically m b cos of theta. Here m is the magnetic moment, B is the magnetic field. And theta is the angle between the two. So we can say, based on this theta, if our theta is equal to 180 degree, so our energy will be maximum. If this theta is our 90 degree, the energy will be 0, and if theta is 0 degree, then this energy will be minimum. So we can use the formula. In the first case, option, or we can say figure 1. In figure 1, theta is 180 degree. So therefore u is equal to minus mb cos of 180, and this will be giving us plus mb. In figure 2, we have theta as 90. So this energy will be our minus mb cos of 90. So this will be coming as 0. And now we come to the figure. We come to figure 3. Here theta is greater than 0 but less than 90, is less than 90 but greater than 0, and based on this you can say that our energy, if it is u, it will be lying somewhere between 0 and between its minus 1, okay, because it is cos 0 is going to have minus mb and cos 90 is equal to 0. And next is our figure 4. Here theta is given as greater than 90 but less than 180. Theta is greater than 90 but less than 180. So therefore we can say that our energy u will be greater than 0 but it will be less than plus 1. That is because of plus mb. So for sure we can say one thing, that we have to arrange it in the decreasing order. So maximum will be at 180 degree and minimum will be at 0 degree. Okay, so let us try to sort it out. So maximum will be for this figure and this will be our minimum. So based on this we have to find out for the decreasing order. So the only option that is correct is option number D is the correct one because it is in the decreasing order. So maximum is our, one second, there is, one second, I made some mistake here. Yeah, so let me draw the, okay, so this needs to be modified, this portion and this as well. Okay, so for this third equation it is given that theta is our on the negative side. Okay. So therefore we can write that our magnetic field, that is our, so not magnetic field but the potential energy is our minus mb cos of theta because theta is our, with respect to, it is greater than 180 degree That was my mistake, but less than 360. And for the last part, this will be our positive MB cos of theta, because here theta is our greater than 90 but less than 180. Less than 180. So only difference between last two will be of the sign. Therefore, we are sure that the magnetic field will be of the order. First one is giving us MB, second one is giving us 0, and but here to be modified, yeah, this one also. So maximum we are sure that one will be maximum only, and so option D cannot be possible. And third will be minimum because it is having a minus of this, and the fourth is having a positive sign. So this will be our minimum because of the minus MB cos of theta, and this is our plus MB cos of theta. Okay, because angle has to be taken in this direction. That was mistake on my part. So therefore, this third will be the minimum. So the only option is the correct one is option number C. So option C is correct. And yeah, here also I have to make a certain change, that this need not to be minimum or theta is equal to 0, because in one of the options theta is 0, but this energy is equal to 0 but not necessarily minimum. Not necessarily minimum. Okay. So sorry for this confusion. And we come to the last part, and in the last part it is said that we have a ring of radius r, uniformly distributed charge q is mounted on a rod suspended by two identical strings. The tension in the strings is in equilibrium is T naught. Now a vertical magnetic field is switched on and the ring is rotated at a constant angular velocity omega. Find the maximum omega with which the ring can be rotated if the string can withstand a maximum tension of 3 naught by 2. In this question, this is the basic figure, and here it is having a string, two strings on the left as well as right, and it said that initially it is having a tension T naught and it is in equilibrium when there is no rotation. And we have a disk and which starts to rotate in the presence of magnetic field, and the distance between the string is d, and we have to find out the maximum value of omega, so that the maximum tension in the string is 3 T naught divided by 2. So initially, when this ring is at rest, the tension in the string is given as T naught. See, the ring is at rest and each string has tension T naught. Now, in the presence of magnetic field, as this circular disc starts to rotate, there will be this rotation is going to generate a magnetic moment, and at this, which interact with the given magnetic field, and because of the given magnetic field, their interaction will exert a torque on the system. So from here also we can say that the rotation generates it is having a charge Q. The rotation generates a magnetic moment which interacts with magnetic field, exerting a torque on the system. Exerting a torque on the system. So as it is going to exert a torque, the tension in the strings, which was initially T naught, in the both the one, it is going to change. On the one side it will be on the higher, and other side it will be the lower because of the rotation. So therefore you can say that due to the torque, which must be balanced, or we can say the torque must be balanced by different tension in the two strings, by different tensions in two strings. Okay. And therefore we can say that because it is moving in clockwise direction, so we can say that the string on left side needs to pull harder, than the right one. So if left side tension is given as our T1 and right side is our T2, so therefore T1 has to be greater than T2, and this is going to balance the magnetic torque. So let's come to the main question now. When you can say there is no rotation, therefore tension on the left side will be equal to tension on the right side Let us suppose that is equal to T naught as given in the question. And this tensions, like we have a, there is no there is a and we have a ring inside. So here will be our T1, which is equal to our T naught, and here also we are going to have T2, which is also equal to T naught, and in downward direction we are going to have our mg. So under no rotation and the system is in equilibrium, our T1 plus T2 will be equal to mg, or we can say twice T naught will be equal to mg, and from here we can write our T naught will be equal to mg by 2. So this is the tension when there is no rotation. Now we find out what will be our magnetic moment, because we have to find out the torque and other thing. So we start with the magnetic moment. When rotating. So therefore we can say our current I will be equal to charge oblique time. Charge is given as Q and time, let us suppose, is T, and we can write in the form of the angular velocity. So this will be coming as Q upon 2 pi by omega. This gives us omega Q divided by 2 pi. Area we already know because radius is given, so we have here pi r square. Therefore the magnetic moment will be equal to m, that is our Ia. We substitute value of I, that is our m is equal to I is our omega q upon 2 pi, and we have our pi r square. Pi cancel with pi, so we get this as omega q r square upon 2. So this is the magnetic moment. Now we can find out the torque on the magnetic dipole. Torque on the magnetic dipole. So which will be about tau is equal to mb sine of theta, and we can say this theta because the magnetic field is in vertical direction and movement will be at an angle of 90 degree. So theta will be over 90, so this gives us a sine 90 is equal to 1. So our torque will be equal to m multiplied by b, and we get this as omega q r square b divided by 2. So this is the value of the torque. Now this torque will be balanced by the difference in the tension. Like I said, if it is rotating, under rotation T1 is greater than T2, and because of this unequal tension we can find out the net tension in the string, and this net tension is going to generate a torque itself, which will be balanced by the torque because of the magnetic moment. So let us call this as a torque because of the magnetic moment, and see net torque from the tension and let us call it is tau t, which will be equal to T1 minus T2. Distance between the two string is d, so this will be d by 2. So these two torque will be balancing each other. So from here we can write that T1 minus T2 is our d by 2 is equal to omega q r square b divided by 2, and this 2 cancel with 2, we get our T1 minus T2 is equal to omega and q r square b divided by d. And we also that because it is vertical equilibrium, when it is rotating we have two equilibriums, rotational as well as vertical. So we can also write that vertical equilibrium therefore T1 plus T2 is equal to mg. So let us call this equation number 1 and this as equation number 2. Now if we solve equation 1 and 2 or simply add them, we can get the value of T1. So we can write from equation 1 and 2, 1 and 2, we get our T1 is equal to mg by 2 plus omega q r square b divided by 2d, and this further gives us our T2 will be equal to mg divided by 2 minus omega q r square b divided by 2d. And we want a maximum omega. We want maximum omega such that maximum tension and between T1 and T2, the tension while the rotation T1 is the greater than T2, so we can such that the maximum tension T1 is less than equal to 3 by 2 T naught, and we already know that our T naught is equal to mg by 2. Therefore we can say that maximum allowable tension T1, maximum allowable tension T1 is equal to 3 by 2 T naught, and we substitute value of T naught. This gives us 3 mg by 4. And now we can just modify equation of T1 because we are only interested in this T1 equation. So therefore we can say that mg by 2 plus, now omega will be our omega max, and here we have q r square b divided by 2d is equal to 3 mg. Now this is quite simple, straightforward calculation, and from here we can write that here we have mg by 2 and here we have 3 mg by 4. So we get this as omega max q r square g, sorry, not g but b, r square b divided by 2d will be equal to mg by 4. This gives us that omega max is equal to mgd, and we get this as 2q r square times b. And we can just make slight modification here, because we know that our T naught is equal to mg by 2, and we can substitute this as that our mg is equal to twice T naught. Therefore we get omega max is equal to twice T naught times d divided by twice q r square b. 2 and 2 cancels out. This gives us a T naught d divided by q r square b. So this is our maximum angular frequency. So these were the 3 questions. Please complete all the 3 questions. Thank you. So here the theta has to be, you can say, our greater than 270. Should be greater than 270. Okay, so it lies between 270 and 360.